I'm Lewis.
Ready?
Yeah, are you guys ready to tinker with Raspberry Pi?
Absolutely.
All right. So hi everybody, I'm Lewis. I'm fairly new to Portland, moved here about a month ago. Basically I'm an embedded software guy. So for many years I had always heard of people playing around with the Raspberry Pi, but maybe not being an electronics newbie, I never actually got one, and because I knew I would just buy one and they would sit on the sit on the shelf. So this was a good excuse to get one and to kind of tinker around with it. There was one part of the Raspberry Pi that was kind of a mystery to me, and that was the GPU. So I'll get the boring slides out of the way. So kind of want to give you a picture of like where on the Raspberry Pi we're going to be looking. All right. So you've got the ARM that runs Linux. The GPU is actually a bunch of different blocks, or what's called the GPU is a bunch of different blocks, and some parts of it are like basically locked up by Broadcom, who makes the chip that is the Raspberry Pi, the BCM2835. So the what's called the GPU is actually a couple of little DSPs. They're called the VPU, and that runs the firmware blob. So how many of you actually have Raspberry Pis and have tinkered around with them? Okay, so like if you look on the SD card, there's that start.elf file. Okay, that's the blob that's running on the VPU. Okay, it also happens that the VPU boots up the ARM. Okay, so without a VPU, you don't even get Linux. You just get nothing. Okay, and then while you're running, the VPU is kind of driving these other components to make things happen. Graphics, or you're playing an H.264 video file or whatever else. Okay, so here's kind of what basically all the images in this are ripped from things I got on Google Images. So kind of here's a picture of that. So if you're running like an OpenGL program, it's talking to this user space library called libgl. It's passing that to this to a stub driver called VCHI. You've probably seen that if you've screwed around with Raspberry Pi at all. It's like this it's like this an RPC, an encapsulation layer. It takes messages and it passes them to and from the GPU. Okay, so like back in 2012. There was this announcement, we're making the graphics driver on the Raspberry Pi open source. And a couple of people looked into it and they said, no, you really didn't. What you did is you open sourced this VCHI part. So, you got a lot of code that's like push this in a ring buffer, or deserialize that. And it's like this has nothing to do with graphics drivers. And then more recently they open sourced more, but still not even close to what you'd consider everything. So anyways. Most of the drivers, the interesting part of the graphics driver happens on the VPU, right? So he's sort of in charge of everything. And Broadcom has basically said we're not going to release that because it has like video codecs. Okay, it has a proprietary RTOS on it. So they're basically saying, all right, guys, if you want to reverse engineer this, have fun. We'll come back to that maybe in a little bit. Some of these other slides are basically just here for reference. And I'm going to skip the first demo because switching over the video inputs is kind of takes a while. So I'm just going to do the two demos one after the other. Anyway, so when we're kind of digging into the hardware, like a really useful question, even if you're a hobbyist, is like, why are we wasting our time doing this? Who cares, right? So somebody out there, it's basically like one person on GitHub has single-handedly reverse engineered like the VPU, some interesting parts of the GPU, basically just by peeking and poking bytes, by using black box reverse engineering. We'll try to write this register and see what happens, and eventually you can kind of figure out which instruction is which and all that. So can we like motivate a better reason than just maybe curiosity to kind of look at reasons why we would look into this or rip apart this closed source driver. And actually, I was hoping to actually make this a discussion, and maybe if you guys have suggestions or things you want to try on the board or anything, yeah, go ahead.
Broadcom recently hired a lead nascent developer to do a 3D stack, and he'll also be doing video mode setting for the chip.
That's great. Is that Herman Hermitage that they hired?
No, it's Eric Anvil.
Okay, I'm not familiar with that name. That's really cool.
Mesa developer.
Oh, okay. So, was he the guy who won there was a competition on doing that?
Nope.
Okay.
He doesn't need to do that.
He doesn't need to reverse anything. He's getting full specs.
All right, I was asking which, if I was trying to connect this to maybe
He's
somebody I
The
know.
most prolific Mesa developer for the last 6
Okay.
years.
Thank you. I'm not very well educated on Mesa.
Yep.
Okay,
So
cool.
there will be a full open source driver for at least to run GLES and to do mode setting
Okay,
for the chip in the next year or so.
cool. I want to come back to that because there's got some other stuff on that. Yeah, so,
I don't know how much of the VPU he's going to be able to document.
right. That's good to know. So another reason is, well, maybe we want people to be able to run OpenCL apps, or if you're an iOS developer, Apple recently released this kind of low-level-ish language called Metal that is kind of used for graphics and for GPU. So maybe you can convince Broadcom that this is a real use case, and people are building applications, and it would be worthwhile just to stoke interest in maybe their brand, or maybe things will go the other way, right? And you'll get all these really smart reverse engineers, and the best ones will just kind of get sucked into Broadcom, and you never hear from them again, And we have systems that work, that do their jobs really well. The hardware and the software are very tightly coupled, but you can't really extend them at all because they're just these monolithic blobby things. Anyways. So yeah, I don't really expect to get into this too much. Just for anybody here who's kind of an architecture nerd, and I wasn't sure if you were even going to be able to read this at all from, but so the VPU is closest in spirit to like a media coprocessor or to a DSP. So he can I think do something like 16 operations per clock cycle, and this picture is only partially representative of what's there. The actual VPU is a dual core, so the scalar unit actually is duplicated. Okay, and I think that the two scalar paths share a vector unit. Somebody correct me if I'm wrong. That's my understanding of it. So, anyways, this guy's really good for doing video scaling or for doing software video codecs if you don't have the hardware block for it. That kind of thing. So sort of like light graphics processing, 2D-ish. It has this really weird vector register file that you can actually address two-dimensionally. You can talk to it in rows or columns, and that makes it really efficient doing like filtering operations, for example. All right. So anyways, the VPU drives the 3D pipeline. So in this, we'll tinker around a little bit with some OpenGL stuff. So the 3D pipeline is basically, you don't have to read all these boxes, basically the top part, which is mostly hardware that's reading in commands from the VPU, these things called control lists, okay? And then it's parsing those, digesting them. It's taking like, okay, I want to draw a triangle somewhere in the right corner of the screen, okay, like in the top right, okay? And then the screen gets subdivided down into tiles, right? They're going to be like maybe 64 by 64 pixels. And the reason why you subdivide it into tiles is because that number of pixels can all fit on chip, okay? And so then you do all the rendering for that one tile all at once. So this GPU splits graphics drawing into two phases. The first where you figure out which tiles correspond to which primitives or basically shapes you told it to draw, okay? The second is we're actually going to draw everything for one tile all at once. So I don't know have any of you heard of tile-based deferred rendering? Okay.
Correct. You're doing good. Yeah. The one trick that they do though is that when they're doing a primitive scanning, they're actually binning them so that the primitives that are going to hit a particular tile get binned into for that tile, and so when they go back and process them, they only run the primitives that are going to hit that tile.
Right. Yeah. That is like the most important point of it is so you don't waste memory bandwidth. Well, this isn't really too much about GPU architecture, but and then the bottom part is the fun programmable part. All right. So these guys down at the bottom, those are the QPUs that were in the earlier slide. So that's actually what we're going to be tinkering with today.
Yeah, believe it or not, tile-based deferred rendering is actually more modern style.
Yeah.
It's not super fancy. No, it's not modern, but for this size of thing, it is. It used to never be in something this size.
No, SGX has done it for a long time.
SGX did it for a while.
Yeah, like Power VR, those guys sort of maybe originated the tech.
10 years or so. It's how you do embedded graphics.
It is now.
It always has been.
Maybe kind of like a new question, but
Yeah.
how does it deal with then, if it's thinking about tiles, then how does it deal with, let's say you want to make a shape, like a triangle or something, but part of that shape is outside of one of the tiles, but not the whole point?
You bin it to multiple tiles.
Yeah, there's sort of an any-to-any relationship there.
The good news is that most modern rendering, it's polygons per pixel, not pixels per polygon. So this works really well.
So are any of you like Intel employees that are working on the same thing? I know they've got their zone-based rendering. That's kind of a...
Zone-based rendering was a disaster.
Okay, I'm curious, but I don't want to get too diverted into that because I actually want to show some little experiments off. Anyways, so I'll probably just skim over this as well. The QPU is it's sort of another DSP, but he's much more specialized for doing shaders. Okay, and this one is a little bit weird to program in assembly because because implicitly you're actually executing more or less 16 instructions all at once, or at least the chip, the core makes it look that way. Okay, and so when we're writing assembly, you're actually going to see one instruction at a time, but you're going to have to imagine that in parallel. It's kind of like when you program in CUDA or any other GPU kind of situation. Except we're going to have one level of pain and difficulty more in that this is just going to be assembly. Some interesting features of this, I guess, if you're an architecture nerd, are these. There are two separate ALU paths, so I know you can't read that. This top guy is like a multiply path, okay, and the bottom is an add path, and each one of these little cores can do both of those at the same time, in addition to some other stuff. But that's the main application. And then there are these two register files, and each one you can read once and you can write once. So that's also a little bit weird. If you're like from your Architecture 101 class in college, you usually saw a register file where you could read two register from and like write one register to. So this kind of keeps the chip small and efficient. And not only that, but there are also some other weird auxiliary registers. There's some accumulators down here, and then there's this sort of mystery window register area that gives you access to the rest of the chip. Like think of like on a microcontroller, you can access random peripherals just as though it were a register. So there are some special register values that you can go out and touch different parts of the 3D pipeline or on-chip memory. Okay, so I'm gonna switch over to the Raspberry Pi, and it's gonna take I think a few seconds for the video to sync. So let's see here. Okay, there it goes. So, boop, boop. Alrighty, so I wanted to show you guys some existing reverse engineering efforts. All of this is basically what this guy, Herman Hermitage, has done. I wanted to kind of show you guys the state of the reverse engineering effort out there on the QPU side. And I'll explain why in a second. So,
Is that his real name?
I don't know. I don't know. That's just his handle, right? Okay, so I've already got a lot of driver code and examples already going. What I was thinking I would try, by the way, can you guys read that well enough? Or if you want to move forward, you can. Okay. So let's try writing some assembly. Now, I'm going to see if I can. So this is like the most minimal hello world kind of example that you can do, okay? And this, so basically what this is doing, so this is running on one of those shader QPU guys, okay? And so what this is doing is it's moving this immediate value of 2. It doesn't need to be 2. Actually, I'm just going to make it 1. I experimented with 2 before just to see what happened. Nothing. So what this is going to do is it's going to notify the host processor that I'm done. So this is basically the equivalent of main and then like return, okay? And then this next instruction right here is thread end, okay? So this QPU is this multi-threaded processor. You explicitly need to give it an end thread instruction, okay? And then because of the way the pipeline works, you actually need to fill in these things called delay slots with no op. So did any of you, are you familiar with that concept? Like, on older CPUs, they couldn't, they couldn't figure out that you had introduced a delay in the middle of the pipeline. You had to fill it in with no ops. Otherwise, things would get, anyway. So this one is like that.
Intel GPU takes 8 milliwatts.
Very cool. All right, so I write that. I'm going to go make clean and make.
Nice. The assembler's written in JavaScript.
Yep. So this fellow has written his own assembler in node.js. Okay, we're just going to assume that it works. All right. So this is going to be a bunch of just hex output, and I will explain what's going on. All right. So you need to run it with sudo because it tries to talk directly to a hole in memory, or I should say a window in memory, so it can communicate with the QPU. So anyways, boink. All right, so what did this do? So it just so happens that we are looking at a window of memory that is the data that we've shared with the QPU, okay? So the format of this is, I'm going to highlight, of course you can't see that. So the first, right up until that point right there, all this stuff, that's the actual shader code we uploaded. So I'm going to make sense of that in just about a second. So let's cat out .hex. So that hex file, that's the output of the file that we assembled, okay? So there it is. So this is the LS 32 bits and then the most significant 32 bits, and they're in that order, okay? So what is it ends in 10009E7, okay?
Second.
Yeah. And then the rest of that, so this line right here, the 001, that is a fixed constant number that we pass to the QPU just as a test, okay? And then this guy right here is the address of your parameter right there. So that's the address of that. And then the address of the program, of the code, exactly. So by the way, this parameter right here in GPU language, that's called a uniform because it's uniform over the execution of the entire shader. Okay? Doesn't change. It's like a constant. All right, so now why don't we go in and kind of poke this a little bit. So one thing that I think will work is if I go and I change this value to a 0, I go make, then I run it again. Did you see that little delay of about a second? I'm going to do it again. So what just happened is that we just hung the QPU, okay? So by writing a 0 to that register, it's like don't signal the host processor. And so on the C program, which I haven't really got into yet, it's basically just timing out, okay? All right, so now what I want to do is, because the structure, the two examples I want to show off are very, very similar, is actually look at the C code for the second one, all right? By the way, does anybody have any questions? Like, or does anybody, more importantly, do you feel like I just dumped a lot of hex numbers at you and you're like, what? Does this make some kind of sense? Okay. All right. So this is just some very messy C code. Let's go over to main. So we're going to be parsing out a parameter. This is a little modification that I made to Herman's program just to test it out. We're going to allocate a window of memory. So remember how I showed you that hex dump? That's what this window is. Okay. It's doing some pointer arithmetic. Here's a handy little picture of this memory. I should have showed you this before. It's just like what you said. You've got the QPU code in the beginning, then you've got some uniforms, and then a pointer to the uniforms, and then a pointer to the code. And actually, you repeat this if you want to start up multiple QPUs, like if you want to invoke it to run on all 12 of them, for example. That last example only ran on one. All right. Then basically we're building up this array. So remember we're just going to concatenate the code. We're going to concatenate the uniforms on top of that, and I'll have a little bit easier to read hex dump to show that. And then we're basically going to print out the contents of the memory buffer before we run it. We're going to run the shader, and then we're going to do another hex dump, and we'll see the difference. And one thing I wanted to look for in this is, so the purpose of this second example is to actually get data back from the QPUs. So the last example, what we did was we basically just ran it and then we had it returned, but it didn't return anything useful to us. So how do we get data back to the host CPU? So the purpose here is that we're gonna take our memory buffer, we're gonna fill it with hex 55s, and then anytime the GPU wrote over any of it, we'll see it. It'll just be visually obvious. Okay. All right. So here's the important part where we actually launch the QPU program, and then we kind of clean up after that. In the interest of keeping to my stated time window, I will not get into the implementations of those execute QPUs quite yet.
If you want to run longer, that's fine.
Okay. Yeah. Any thing that you're curious about too, we can try. All right. So now let's look at the assembly. This one there's a little bit more that's pre-written here. So let's make sense of this mess right here. So there's something like an assembly macro up top here. All right, well, we're going to ignore that for a second, just for a second. So what this shader does is, you remember the uniform value that I talked about? That was the parameter that we pass in from the C program. It should be clear that there's not just one uniform. There can be 16. There can be however many you want. Okay, and there are other ways of talking to the chip. Anyways, so this shader talks to a piece of on-chip memory. It's called VPM. It stands for vertex parameter memory, if I remember right. Think of it just like a piece of on-chip memory. So what we're going to do is the shader is going to read some data from our user program. It's going to scribble on the VPM. This is this on-chip memory, and then it's going to blast that back via DMA to a shared memory window, which we'll be able to see. Okay, so you need those two steps. You need whatever computation you're going to do right here. In this case, we're just writing to the VPM, and then we're going to do a DMA transfer back, and that's this stuff. Okay. Then you've got a couple of other instructions like this guy, this move never v. So what this does is this is actually waiting for that DMA to finish. So there's remember I said there were like some special registers that have some weird functions. Anyway, so that's going to wait, and then we're going to signal that we're done. All right. So, go ahead.
Is the signal so that the other CPU knows to read that memory, or?
Yeah. So in this case, the other CPU is us. It's the ARM, right? So that. Repeat your question.
So that it doesn't like read the memory when it's like half written.
Right. And there are a lot of other mechanisms that this chip exposes, like semaphores and mutexes and so on, to kind of help solve that type of problem. But this is like the most primitive one. All right? And at the end, we just signal that we're done, just like the other one. All right, so let's see here. Now, we have to pass it a uniform value. So I think what I'm going to do is pass it like dead beef. All right, so hang on just a second. So So this is the before array right here. And in the top, you can see the machine code for our shader, and then you've got our uniform value right there, right? Then you've got a another uniform value, which is a pointer to the buffer that we're going to want to fill. And then you've got the other two pointers. You've got the pointer to the uniform and the pointer to the code itself. All right, so scrolling back down, I can manage that. All right, so this is the snapshot that we took after. All right, so we'll just sort of remember the pattern here, right? So it's like 0 dead beef, 1 dead beef. All right, so now let me cat out the boink. So the important part of this is that right here, we're moving the element number, and this is another magic register. That's which slice, or I should say, which part of the QPU am I element 0, am I element 1, am I element 2? Writing that into the VPM, and then writing our uniform value in. So,
Where is right here?
right, Let me see. I'll show you in a second. Sorry. All right, so what we're going to see is the element number followed by the uniform value that we passed in, okay? And then that's going to get repeated by the number of elements in a QPU slice, okay? So I'll run it again, and there we go. So we've got element 0 telling us dead beef. We've got element 1 telling us dead beef, and so on, okay? So let's try something else. So let me see here. Let's look at another example here. So this is something I was tinkering with because that wasn't really all that interesting of a shader. I wanted to try out some branching behavior, for example. So what this guy's basically going to do is he's going to take the uniform value that you passed in, and like if you pass in a 5, what it'll do is it'll sum 5 plus 4 plus 3 plus 2 plus 1, and then it'll write. So and then it'll give you that value for that part of the shader. Okay, so it's just a little loop that if you've ever done any assembly programming in school or whatever, you had to write something like this. So somebody who isn't well versed in these things, why is that there? Why are the NOPs there?
License.
What's that?
Sorry. Somebody was a builder.
Padding, or because the pipeline needs to run out?
Right, number 2. But padding is also a good answer. I like that. Right, so branch instructions on the QPU are, the later part of the pipeline doesn't know, like by the time we're here, it doesn't know yet that we've branched, right? It doesn't actually know until like 3 cycles later, okay? So you have to put in some no-ops there. All right. So now I'm just going to...
Code following doesn't take care of that for you? 'Cause
The-
you have code bytes following.
Right, so
And you don't want to execute those till you're done with the loop or that.
so if I didn't have those no-ops, then those would get run no matter which way the branch went. So
Gotcha.
right.
So you can actually embed branch instructions that should be executed before the branch, after the branch. Usually
Right.
we put an instruction in the license.
Yeah.
Exactly. Right. So did you guys understand that? So I could have taken some instructions that, if I had more instructions that need to be inside the branch, okay, I could have pulled those and actually written them after the branch instruction. All right. So I'm just going to blow away the example that I had there. Do make. Hopefully. Oops. I hope it does, but if it doesn't, I would actually like to have a live debugging session.
Looks like it worked.
Yeah, so that's
You gotta have fun.
15, right? All right, so now let's
Absolutely.
run it again. There, I just passed in a 4 that last time. There's 10. Okay. Let's see what happens if I pass in a million. This is something I haven't tried.
Or even-
Okay, so we got some kind of overflow or something, but it's still finished, right?
And it gave the same answer on all of them, so that's what you wanted to see. Yep.
Yeah, that's another. So I was kind of curious. This took 100 milliseconds to run to count to a million. So what if I say count to 2 million? Okay, that took around 200 milliseconds. Huh. So what if I give it 16 million? Oh, and I got a delay there. So there's a limited amount of time that anyone has at the end of the day to tinker around with this kind of stuff, right? Like this is just part of a piece of the stuff that this guy Herman has, or whatever his real name is, has worked on. It's just a hop and a skip away from like, let's run an FFT on the shaders, or let's run SHA, 256 hash or something like that. And if you like, I actually have those examples on here. I can run them, but what they do is they say, okay, I ran, all right? And I didn't get a chance to visualize, this thing like, oh, it's really slow with the, running on the CPU, and it's significantly faster on the QPU. The main hurdle to kind of to actually making this useful right now is there's a synchronization delay. So I'm going to go back to the first example. All right. This example does almost nothing, and it still takes 82 microseconds to poke the GPU with a program that has nothing in it and to come back. All right. So at most you can do like something like 10,000 invocations per second. So you need to batch up work, blah blah blah. All right. It would be faster if we had a way to have a driver running, an open source driver, like you said, running on the VPU, okay, and then it might make some sense.
Oh, you're actually telling the GPU to run this stuff on the QPU.
That's a good point. Yeah, that's absolutely true.
I think Eric's plan is to not use the GPU to drive the GPU.
Okay, so I guess I'd like to come back to what I said I wanted to come back to. So there was this open source competition recently where it said, okay, we're releasing the source code to the graphics driver on a completely different part. It doesn't have a VPU, but it does have the same 3D pipeline. See if you can make it run on this chip. And somebody did, and it kind of ran at playable, like for a game, it ran at playable frame rates. And so they actually managed to get by without the VPU at all, or by just passing things through the VPU without having anything running on it. Okay. I'm not sure if that has anything to do with the hiring job that you mentioned before. Is that a completely separate effort?
As far as I know, it's completely separate.
Okay. All right.
Eric was not involved in that particular. He couldn't be because he worked at Intel.
Got it. Okay. So last thing I want to try is to show you another little debug toy. This was actually supposed to be my demo one, but we'll see here. So source hello pi hello triangle dot. All right. Have any of you guys run this? I don't think you need a sudo for it. So this is just a little graphics example right here. All right. So now what I'm going to do is I'm going to Control-C out of that. I was hoping to be able to show you two displays at once, but that's okay. So there's this command, sudo vcdebug. All right, it gives you little debug commands. All right, and there's this command. This shows you the heap, and this is going to be kind of hard to read. So this is showing you basically various chunks that are owned by the VPU. Okay, like there's this guy right here, shader code, and there's various dispatch queues, and if you had textures on there and all, you could. All right. So what you can do is you can start up an example. Let's see here. So I'm going to start this up, and then and I can't show you this, but I'm going to open up another SSH session right now. I'm going to rerun that command, sudo cdebug reloc, and there's a chunk of memory in there. Now I can actually see the chunk in memory that corresponds to some of the textures or pictures that are drawn on the side of this cube. And you can use commands like sudo vcdebug trash is one. Let's see if I can make this trash. There he goes. Okay. So what I just did is I wrote a counting pattern over that texture right there, If you look at the pattern, you can see it looks like a counting pattern. Okay. So now what I'm going to do is switch back, and so this was the command that I had entered over there. It was that guy right there. All right. And that magic address right there, basically I found a chunk that says I'm a texture, and then I just said, okay, scribble all over it. But you're not going to get too far. Like if you try to scribble over like shaders or something, sometimes you can make something interesting happen. Like, oh, instead of seeing a nice shape, I see it's all turned pink, or the shape gets messed up. But more likely than not, it's just going to freeze on you, and then you're going to have to reboot the Raspberry Pi. And I wasn't able to make that completely deterministic. So let's see. Anything else? I guess that's it. I can point you guys to the resources that that I used for this. I can also here. Let's see here. I'll show you my last slide here that has these URLs. Or if you just go on Google and you can look up this guy's handle, Herman Hermitage. These are the two projects. So we didn't really get too much into the what's the VideoCore proper, the VPU. Okay. And the reason is because if we had done that, then this thing wouldn't even boot up. I wouldn't be able to show you graphics. I could maybe make some characters come out on the LCD, but you couldn't really interact with it the way you would for a real system. So I kind of tried to compromise. I'm like, well, is there a piece of this that we can experiment with? And I'm kind of curious, has anybody here done like OpenCL or anything like that on a mobile platform? Any kind of, like mobile GPU? Has anybody experimented with like Metal or anything like that? Or at all with the Raspberry Pi? I'm kind of curious of, other projects to try out with this. Like, I could also try getting FFTs up, or I could try getting, try doing Bitcoin mining or something like that. It might be fun. I don't know.
The nice thing about your shop plan is that you do a hash function, it's easy to get the one big word out of the thing. It's an easy one to pass the data result back.
Yeah. That wouldn't require any kind of fancy queuing or. Yeah, sure. Yeah, I mean there are examples out there, and you can try it without even without installing anything. There's an FFT example. But they don't have the source code for the shaders. This guy Herman went in and kind of disassembled them and commented one of them. Okay, so anybody have any questions or comments or I don't know. I was a little bit dicey on this because it's basically a lot of machine code manipulation. But it was a part of the Raspberry Pi that was like completely mysterious to me. I wanted to cover at least something in a little bit amount of time.
This is an assembly users group. It's completely appropriate.
Okay.
Yeah, it's awesome. Nice talk.
Thank you. All right. Who's the next speaker?
Oh, thank you. Thank you.
Thank you.
Any questions or?
How many people are reverse engineering this, would you say, or is this one guy who?
I think it's probably like 1.5.
I'm just suspicious that the guy probably works there. Or,
All of the mobile
Yeah.
GPUs have been reversing.
Yeah. Bet you that's not a real picture.
Yeah, who knows whose picture that is?
This is real.
Oh no, all of them have GL drivers running on.
Oh, do they?
Reverse engineer. Yep.
Oh, that's cool.
Everything but SGX. Nobody cares anymore. SGX.
I did notice that if you look at like the git commit history, on this guy's, it's kind of tailed off, but and I don't know if this is anything to do with what you mentioned, but there was a comment made by somebody from Broadcom that they were going to be releasing a minimal open VPU blob, but I haven't seen anything on that since February. I mean, they don't have anything on compilers, assemblers, tool chains, anything like that.
When Eric went to interview with them, so
Okay.
they may have been saying, "Oh, we're going to hire this guy, and
Okay.
we're just going to let him do all of that."
Okay.
So I have no idea when it's going to be able to release it. But as far as I know, it's going to be able to, it's a full OpenGL, desktop OpenGL, and GLES stack for the GPU part of this.
Mhm. So I think ultimately this was, the most interesting, basically because there's a lot of guts, the low power architecture and all that this kind of is, is good for educating, basically any kind of digital architecture you want to keep the power down. This is a good example of how to do it,
Also a good introduction to GPU architecture. 'Cause
Sure.
It's very similar to other GPUs.
But maybe a little simpler.
A lot
The
simpler.
desktop
Mhm.
GPUs, yeah. A lot simpler.
Okay. Very good.